All right, hello everybody and happy Friday. So what we are going to do today is we're going to be starting to apply our stoichiometry rules to solutions and a variety of solutions. So the math side of things isn't going to be too much different than what we have seen in the past with our stoichiometry. However, just the types of questions might change just a little bit. So there's going to be three main rules that we are going to need to follow while we are doing our stoichiometry questions involving solutions. Our first rule is pretty much applicable with all of our stoichiometry, not even just our solutions, but always use a balanced equation. And with our balanced equations, we now know a couple different ways that we can write our equations. So some questions are just going to require just a typical balanced equation. However, other questions, especially if they're asking us for ions, right, or anything to do with these ions, we are going to have to write a net ionic equation. And that is because sometimes they're going to ask us questions that may result or may reference one particular ion, right? Maybe not necessarily the entire thing, because sometimes our entire solutions or entire compounds involve multiple ions, some of which that are just spectator ions, and they're somewhat irrelevant to the actual reaction itself. So some are going to ask you to very specifically talk about the individual ions that will impact the overall reaction, how it may occur. The next thing, and this is more so just an equation that we have to make sure that we remember, is our equation for concentration. As you know, a lot of the times we deal in moles, but sometimes we're not going to be given the number of moles that we have in a certain solution. So instead we may just be given something like we have a 0.25 mole per liter solution, right? And we will say we're given, let's say, 1 liter of that solution. So we need to be able to convert from 0.25 moles per liter and given a certain volume in order to determine the number of moles present. And we're going to do that using our concentration equation, which is just C equals our number of moles over our volume. So here, a lot of the times this is how you're going to use it. We can actually fill in here. So we have our concentration, our C value here, which is going to be 0.25 moles per liter. And that's going to equal our number of moles over our volume, which is 1 liter. Now be careful when you're ever using this equation, you have to put your volume in liters. So if you're given 0.5 liters or 500 milliliters, you always have to record it as 0.5 liters. The reason for that being is that our concentration is in moles per liter. So if we use milliliters over here, these units are not going to cancel. So we have to make sure that we're always using liters in the bottom, all right? Always use the exact same thing. And then we could simply rearrange this equation by multiplying both sides by 1 liter. So that would equal 0.25 mole per liter times 1 liter equals our number of moles. So our number of moles, our liters would cancel out, and our number of moles would just equal 0.25 mole. So with that being said, we'll get some practice using this today. I know we've already used it a few times before, but just keep that equation in the back of your mind because it will be rather helpful moving forward. And finally, our third rule, and it kind of is given up here in our first balanced equation, is use your coefficients. So in our balanced equation, making sure that we're using our coefficients, and this is mainly going to be so that we can determine our mole ratios. All right, so all of this really isn't anything new. We have seen this in our past stoichiometry questions. So what we'll do is we'll just jump right into it. We'll get into our first question here. A lot of these questions are written out and they do involve quite a bit of words. So a really important thing that I like to do, especially when I am going through one of these questions, because there is a lot going on, is underline or highlight the things that we think we'll need to use. So a student measured 100 milliliters. So as soon as I see any numbers, right, I'm going to underline them. Same thing with any either word formulas, all right, or actual chemical formulas. Just so then that way when I go back to look at the question, I can easily see, okay, where is everything that I need to know? So they had 100 milliliters of silver nitrate and they added pure copper or Cu, all right, and waited several days. Once complete, the reaction yielded 1.65 grams of solid silver. So as soon as we see a solid going in on a reactant side and a solid coming out on our product side, we can basically guarantee that this is going to be a single displacement reaction. And what we're looking for is the concentration of our silver nitrate. So that's basically going to be what we're looking for in this specific question. And like we said in our rules, the very first thing that we're always going to have to do is make sure that we are writing out our balanced chemical equation. So what we're going to do, we have silver nitrate, so AgNO3, which is aqueous, which is going to be reacting with pure copper, which is going to be in the solid state, and that is going to be reacting to produce, so it's going to be a single displacement reaction. So again, we are going to see our cation ions switch with each other, so our Ag and our Cu, and they are actually going to switch with each other in order to create copper nitrate, which is going to have NO3 2, and we're going to have pure silver precipitate out of that equation, or out of that reaction. And so in this reaction here, lucky for us, right, there's only a couple little things that we need to do. So because of this NO3 over here, because there are two of them, we're going to have to accommodate for that on the opposite side of the reaction. So we can just look where our NO3s are. They're in our silver nitrate. So I'm just going to put a 2 there. And once we do that, I just need to accommodate for that 2 of our silvers over here on this side. So I have 2 AgS that are going to be produced, right? Now we can use this balanced chemical equation and we're going to use it throughout the reaction, but specifically we're going to mainly use it for our mole ratios. So when we're looking for anything, especially with our concentration, it's always good just to think automatically, okay, how many moles do we have that are going to be produced? So here, if we look, we are told that 1.65 grams of solid silver are going to be produced. So we have all the tools that are required in order to convert that 1.65 grams of solid silver into a number of moles. So 1.65 grams is what we're given of Ag solid, all right? And we can put that into moles. So if you look on the periodic table, you'll be able to find the molar mass of silver just under its atomic mass. And that is going to be 107. So our big M, or our molar mass, equals 107.87 grams per mole. All right. Now we have our mass, or this is going to be our little m. We have our big M, right? So we can now use our mole equation, which is our number of moles equals our mass of the compound over the molar mass, right? So we're just going to sub this value in for M, this value in for our molar mass. and that's going to be 1.65 grams divided by 107.87 grams per mole. And as we know, the grams are going to cancel out, and we're just going to be left with moles. So I'll just pull out my calculator here. Hopefully you guys can see this. I'm going to take my 1.65 grams, and I'm just going to divide it by my 107.87 grams per mole. And that is going to give me a rather small number, 1.53 times 10 to the negative 2. So I can just take that, and that's going to be our number of moles. So it's going to be 1.53 times 10 to the negative 2 moles. Right. If you want to write this as 0.0153, that's fine as well. I just prefer to do scientific notation, just keeps everything a little bit cleaner. And then next up, we have our number of moles. So now we can work from that value in order to determine, it's asking us our concentration of AgNO3. So the very first step to determining concentration is obviously knowing how many moles are going to be present. So I can use my molar ratios given my balanced chemical equation in order to determine how many moles of AgNO3 there are. So this here is going to be the number of moles of my silver, which has a coefficient of 2. And what I am looking for is the number of moles of my AgNO3. And conveniently, that also has a coefficient of 2. So I know that between my molar ratio, my ratio is just going to be 2 moles of AgNO3 for every 2 moles of my AgS. It's going to be aqueous, and this is going to be solid. So knowing that, all right, we're always going to put what we are looking for. So in this question, it clearly states that we are looking for our AgNO3, right? So here we go. We put what we're looking for on the top, right? And we're going to set that equal to, so if there's 2 moles of AgNO3, there are always going to be 2 moles of silver. So if I have 5 moles of AgNO3, I'm going to have 5 moles of silver, right? So this ratio of 2 to 2, or you could simplify it to 1 to 1, is always going to remain true no matter what happens. So now I'm just going to sub everything in. So it's going to be equal to, well, we don't know the number of moles of AgNO3. So I'm just going to put X moles of AgNO3 aqueous over 1.53 times 10 to the negative 2 moles of Ag, right? Now, as we know, and we've done many times before, in order to solve for this X value here, all we have to do is we have to multiply both sides by 1.53 times 10 to the negative 2 in order to solve for our AgNO3. So over here, I'm just going to write a new equation. I'll write it in green so we don't get mixed up. It's just going to be 1.53 times 10 to the negative 2 moles of Ag times 2 over 2, which is just our molar ratio from over here. And what that's going to give us is that there are also going to be 1.53 times 10 to the negative 2 moles of AgNO3. And that makes sense to us because if it's 2 to 2, we can basically assume that it is always going to be the exact same amount of moles of our Ag that are going to be produced as we put in of AgNO3, assuming that we have an excess of copper. So what we'll do is just now move on to the next step. We're almost there. So now that we have our concentration of Ag, or not our concentration, our number of moles of AgNO3, which equals 1.53 times 10 to the negative 2 moles, we can use that equation that we talked about before, our concentration equation, where our concentration equals our number of moles over our volume, right? And we can solve for our concentration. And if we look back to the original question, right, we measured out 100 milliliters of our silver nitrate. So what we can do is we can take that 100 milliliters and we're going to sub it in here for our V. So our V is going to equal 100 milliliters. But we can't input that into this equation because we are dealing with concentration in moles per liter. So I have to convert that to liters. So 100 milliliters is going to equal 0.100 liters. So if I have I have my number of moles, I have my volume, so now I can just solve for my concentration. So my concentration is going to equal 1.53 times 10 to the negative 2 moles per 0.100 liters. And some of you can do this in your head, but for the others, 1.53 times 10 to the negative 2 divided by 0.100 moles per liter is going to give us 1.53 times 10 to the negative 1 moles per liter. So our concentration is going to equal 1.53 times 10 to the negative 1 moles per liter of silver nitrate. Right? And we're done. That's our final answer there. So you could write a word equation or a word sentence there to describe what you have found here. However, this will suffice, just saying 1.53 times 10 to the negative 1 moles per liter, or if you prefer, you can write it as 0.153 moles per liter, whatever you prefer. So moving on, we'll have another question here. Essentially a lot of the same processes. However, this time we are not going to be looking for the concentration of a solution. Now we're going to be looking for the concentration of ions. Okay? So whenever we see this word ions, we're immediately going to think ionic or net ionic equations. Okay? So what the question is asking us is saying excess lead-2 nitrate, or PbNO3 is added to 125 milliliters of sodium iodide solution, or NaI, and the precipitate formed has a mass of 4.13 grams. What is the concentration of iodide ions? Okay, so always, our very first step is always just going to be writing that balanced equation. Right? Once we have that balanced equation, converting to our net ionic equation becomes a lot simpler. So our balanced equation, right, we are going to have PbNO3 2AQ plus NaI, or a sodium iodide, and that is going to produce, right, a precipitate, right? But we're not too sure what this precipitate is. So if you go to your solubility table, you will be able to determine what that precipitate is. When we see two components on each side, two ionic equations, we can automatically think that this is going to be a double displacement. However, sometimes you may have to check your solubility table in order to figure out what your solid precipitate is going to be. So I'm just going to write these out first without states, and then we'll include the states after. So it's going to swap out our cations and our anions. So we are going to have PBI, and that is going to be PBI2, because this NO3 or I is going to have a charge of 1 minus. However, our PB is going to be lead-2, so it is going to have a charge of 2 plus. And that is going to be produced along with sodium nitrate, NaNO3. All right. So with these now, if you've had some time to go look at your solubility table, you will notice that lead and iodide together are not soluble. So that is going to be our solid precipitate, right? And our NaNO3 is going to be aqueous. Now using this equation, we can now determine our net ionic equation, right? I always like to write the ionic equation first and then cancel out our properties that we have after. So I'm just going to write everything out in a whole ionic equation, and then we'll cancel things as we need in order to get to our net ionic equation. So first I'm going to look here. My Pb is going to be a 2 plus our, we should have balanced this before. So this is going to be 2 NaI, and then we're going to have 2 NaNO3s over here, just because of this 2 here, right? And then we're going to have 2 NO3s because we have this extra coefficient down here. So we're going to have 2 NO3 minuses, right? Plus 2 sodium, Na plus 2 iodine. And those are just going to be a 1 minus. And it is going to react to produce lead 2 plus. Actually, no, it won't be lead 2 plus because this is our solid. So we're just going to leave PbI2 in there because it is now reacted and become a new compound, plus our 2 Na and our 2 NO3. And that is going to have a charge of minus. So once we have this, then it's really, really easy to get into our net ionic equation. We're just going to cancel our spectator ions, or the things that are on both sides. So I'm going to take my NO3 here, because I see it on this side as well. Cancel that, cancel that. Also my 2 Na plus, I have 1 on each side. I'm going to cancel that. And now we're going to see that everything lines up. So we can just transfer everything down. Pb2 plus 2I minus is going to work to produce PbI2 solid. And there's our net ionic equation. So we have that, and that is going to be very, very helpful once we need to look at our molar ratios. But for right now, it's asking us again, we'll determine the number of moles of our precipitate. Right? So now we know that our precipitate up here that produced 4.13 grams is obviously going to be our lead iodide. So I can just take that and I'm going to put it into my mole equation. So my number of moles is going to equal my mass over my molar mass. Right? Our mass was determined up here to be 4.13 grams. Right? And if you look on the periodic table, your molar mass, or your big M, is going to equal 461 grams per mole. And just a side note, it does make sense that this is going to be insoluble because it just is so large. And we can see that in the molar mass. So our moles is going to equal 4.13 grams over 461 grams per mole. And that is going to equal, if we punch that into our calculator, 4.13 grams divided by 461 grams per mole, going to give us 8.95 times 10 to the negative 3 moles. So 8.95 times 10 to the negative 3 moles. So with that, we can then take it down and we can use our molar ratios in order to determine our number of moles of iodide ions. So this here is going to be our number of moles of our lead iodide. So what we can do is we can use our ratio between iodine and lead iodide in order to solve for the number of moles of iodine. So here, we always put what we're looking for on top. So we're looking for iodide ions. So our ratio, our molar ratio from iodide to lead iodide is going to be 2 moles of I minus per 1 mole of lead iodide. All right, and we can set that equal to our number of moles of iodine in our final solution, divided by our number of moles of lead iodide, which we calculated up here to be 8.95 times 10 to the negative 3. So I'm going to take this, right? So I'm going to have X moles of I minus over 8.95 times 10 to the negative 3 moles, right? And then I'll put it in a different color again. We are going to rearrange this equation. So simply we're just going to take this and multiply it by our molar ratio. So we are going to have 8.95 times 10 to the negative 3 moles of PbI2 times 2 moles of iodine over 1 mole of PbI2, right? Our moles of PbI2 are going to cancel, so we're only going to be left with moles of iodine. So if I take my calculator, I'm just going to take 8.95 times 10 to the negative 3, and I'm going to multiply that by, in brackets, 2 divided by 1, which is going to give me 1.79 times 10 to the negative 2 moles of I minus. All right, so now we've calculated our number of moles of I minus. So again, we just have to take that value, so 1.79 times 10 to the negative 2, which is going to equal our N, right, or our number of moles of iodine, I minus, all right, and then we can put that into our concentration reaction. So if we look here again, we see that we had 125 milliliters of sodium iodide, right, that was added. So our concentration is going to be equals our number of moles over our volume, right? Exact same equation. So I'm going to take my number of moles, which is 1.79 times 10 to the negative 2 mole of I minus, and I'm going to divide that by my 125 milliliters. Of course, I have to convert that into liters, so it will equal 0.125 liters. All right, and if I do this calculation quickly on my calculator, luckily I already have my 1.79 times 10 to the negative 2, so all I'm going to need to do is just divide that answer by 0.125, which is going to give me 1.43 times 10 to the negative 1 moles per liter of I minus, okay? And that's going to be your final answer, all right? So hopefully these two questions have explained how to do these problems quite good. However, if you need to, feel free while you're going through these practice problems to pull up the video on your laptops and skip to certain spots where you may be having trouble. So what I want you to do for the next kind of 10 to 15 minutes, right? On page 417 of your textbook, please complete the questions 11 to 17 and number 20, or get as far as you can. You may have to do some for homework, and then return for part 2 once you're completed. Thank you.